Good morning, everybody. Welcome to a rainy, overcast Wednesday morning at Chem 1211 with your host, me, Dr. White. All right, as I mentioned yesterday, and I'll send out an email to remind you, next week, Monday through Thursday, you should go to the testing center at College of DuPage, COD, and take test number 1. You'll need a photo ID, and let me grab this. And I take my calculator too. You can bring your own calculator, and you can bring a graphing calculator. In the past, faculty didn't allow that because students would, this is not a graphing one, but students could input things in a graphing calculator to cheat. Well, I've eliminated that possibility. How? Well, the things students used to cheat on, which would be the formulas, I put at the back and important information for my tests and quizzes too. So, excuse me. Remember, you have Monday through Thursday, end of the day next week, to take test number 1. And go take it. What more can I say? You will need a photo ID. Like I said, bring your own calculator and obviously some writing implements. I would take a pencil and get a good eraser. All right. I promised today, so I'm not going to lie to you. I will do review for test number 1. In fact, this morning I uploaded it to the testing center so they can give it to you. And I highly recommend, before you take it, go look at, well, first of all, do the practice problems if you have it, and go look at the important information, test number 1, because that will be given to you. All right, let's go through the review. All right, everybody see test number 1 review? All right, we talked about last test, and I don't put things overlap, but you should know, an atom has protons, neutrons, and electrons. And the question is, where are the electrons? Well, they're in the shells on the outside. And the shells are called shell 1, 2, 3, 4. This will be given to you. Now, the number of shells and subshells in shell 1 are 1 and 1, 2 and 2, 3 subshells and 3, 4 and 4. Now, the subshells have names, and they're actually letters, but those are the names, and it's S, P, D, and F. And by the way, let me write something which I don't have on here that you have to memorize. And shell 1 is the lowest energy shell. As you go down the table, you go increasing energy of the shells and electrons in the shell, and shell 4 is the highest. Now, the shell names S, P, D, and F, and S is the lowest, F is the highest. And each subshell, there's a maximum number of electrons you can put in there. S, you can only put in 2, P, 6, D, 10, F, 14. Now, how do you show where are the electrons? Well, for my course, I'm asking you to learn electron configuration. That's the statement of how many electrons an atom has in each of its subshells. Remember, a subshell is named by a number and a letter. Example, shell 2, the first subshell is 2s, not s, 2s. And when you do electron configuration, we do numbers and letters and subscripts. And let's do a quick one. First of all, let me open something else important up. All right, everybody see the periodic table on your screen? Oh no, it's not there. Hold on. Oh, it is. Thank you, Gianna. All right, you will be given this exact table. It won't be in green, it'll probably be on white paper. When I had these printed up, I had them in green. And when you're doing the electron configuration, you need to know how many electrons you're dealing with. How do you determine that? You look at the atomic number. The atomic number, the number in the upper right-hand corner, I like that special effects. Uh-oh, it's Bad Humor Wednesday, is how many electrons. Hydrogen has 1, lithium 3, oxygen 8. And let's look at, oh, my favorite, one of them, nitrogen. And if I were to ask you to draw the electron configuration of nitrogen, first thing you'd have to do is find out how many electrons does nitrogen have. If you look at the periodic table, its atomic number is 7. Now, I don't have to look at the table. The first shell is 1. The first subshell, there's only one subshell in 1, is 2. The maximum number of electrons I can put in s orbital, I'm not orbital, subshell, is 2. Well, I got 5 more to go. There's only one subshell in 1. I filled it up. So now I have to go to shell 2, and the first lowest energy subshell in shell 2 is S. And let's see if and if you look, remember, and atoms always fill the lowest energy shell and subshell before they go to the next lowest energy shell and subshell. So the shell 2 has 2 subshells. The first one is 2s, the second one 2p. S, I can put 2 electrons in max, p, 2p, 6. So if I go back here, I have the lowest energy subshell in shell 2 is 2s. I can put a maximum of 2 electrons, and I did. Well, 2 plus 2 is 4. 7 minus 4 equals I have 3 more electrons to go. And now I go to the next lowest subshell in 2, and that's 2p. Remember, a subshell name is a number and a letter. And I can put up to 6 electrons in 2p, but I only need 3. So I've done that. And that's how you do electron configuration. And notice I have the hint. Next, we talked about, notice I say we, I did, you listened and watched on the video if you weren't here live. I better say hello to everybody out in YouTube land. It is Bad Humor Wednesday. Next, the valence electrons. You should know that the valence electrons are the outermost electrons of an element. And that's the definition you should know. And how do you determine the number of valence electrons an element has? You look at the periodic table, and the number on top, it originally, like this periodic table, had it in Roman numerals. So I found out a couple of years ago, they don't teach that in school anymore. But so I wrote the numeric number. And if you look at how many valence electrons does hydrogen, lithium, or sodium have? 1. How many valence electrons does carbon have? 4. How about oxygen? Number on top, 6. And if we keep on going, say neon has 8 valence electrons. So the number on top of the column of the periodic table tells you how many valence electrons an element has. Now, you should know how to draw the Lewis structure for an element. You use the element's chemical symbol. We only use valence electrons, and you put 1 valence electron on each side before doubling up. Next, I talked about chemical bonds. Those are the forces that hold atoms together in molecules. There are 2 types of chemical bonds, and you should know the definitions. For an ionic bond, that's the results from the transfer of 1 or more electrons from one atom or group of atoms to another atom or group of atoms. You should know this. A covalent bond, what is that? And that is, it results from the sharing of 1 or more pairs of electrons. Remember, pair means 2. Now, the octet rule, which I'll never, ever ask on a test or a quiz, is in a compound formation, making a molecule, atoms of elements lose, gain, or share electrons in such way they have their electronic configuration identical to that of the nearest noble gas in the periodic table. And if you remember, I just showed you, all noble gases have 8 valence electrons. That's the most stable. Now, when we talk about covalent and ionic bonds, if a compound loses or gains an electron, it forms an ion. And here, elements lose or gain electrons to have the same number of electrons as the nearest noble gas. So if I were to ask you, what ion does calcium form? Well, calcium, you look up on the periodic table, has 20 electrons and 20 protons. Now let's go to the periodic table. Here's calcium at 20. What's the nearest noble gas? Remember, noble gases are the elements in the last column all the way to the right. I like those fancy special effects. Oh, it really is Awful Wednesday, Humor Wednesday. And if we look at 20, which is closer numerically based on atomic number, argon at 18, 2 away, krypton at 36, 16 away. Well, I hope you all picked 2 away. So calcium wants to have the same number of electrons as argon, 18. So here I have 18 electrons, but it still has the same number of protons. And there are 18 electrons. Each electron has a -1 charge. You get -18. There are 20 protons. Each proton has a +1 charge, +20. Add these together, -18 plus 20 plus 2. And the answer is not this, it's this or this. When I ask what's the ion, an ion is shown by a chemical symbol and the charge on that ion. And you can also have -2, which we did. All right, now, charge balance in ionic compounds. The formula of an ionic compound indicates the number and kind of ions that make up the ionic compound. And I probably should have had this in red. You should remember the sum of all ionic charges in a formula is always 0. And let's do a quick one. What would be the empirical formula or chemical formula, either one I can put on test, for a molecule with calcium +2 and bromine -1? Well, this is a +2. This is a -1. All molecules have a net 0 charge. That's got to add up to 0. And if we look here, we can't change the charge, but we can change how many we have. And if this is a +2, we mean this to be a -2, so 2 times -1. Now, how do you show the formula? This tells you there's 1 calcium and 2 bromine. And that's how you do it. And I also showed how to do it with polyatomic ions. Now, when we talk about covalent molecules and ionic covalent molecules, and I'm about to sneeze, excuse me. Excuse me. That was a super slow motion sneeze. But anyways, back to chemistry. We have in Lewis structure for molecules, and again, whenever you see the name Lewis, that means valence electrons. And therefore, when we have in a molecule, you have bonded electrons. Those are pairs of electrons that are shared between atoms in a covalent bond. And you have non-bonding electrons. Those are pairs of electrons that are not involved in electron sharing. And when we talk about covalent bonds, you should know. Oh, let me be subtle. For a covalent bond, there are 3 types. Single bond, you have 1 pair of electrons. Double bond, 2 pairs of electrons are being shared. And triple bond, 3 pairs of electrons. Remember, a pair means 2. So you should know what are the 3 types of covalent bonds. Single bond, and you should know how many pairs of electrons are involved in that type of covalent bond. Single bond, 1 pair. Double bond, 2 pair. Triple bond, 3 pair. I can do that with my right hand too. Single bond, 1 pair. Double bond, 2 pair. Triple bond, 3 pair. By the way, I'm ambidextrous. I'm also Dr. White. Oh, that was bad. But meanwhile, let's continue. And let's do one of these. If I were to ask, draw the Lewis structure for ammonia. Now, first of all, Lewis structure means valence electrons. And so if you look at the periodic table, nitrogen has 5 valence electrons, hydrogen 1 valence electron. And the only way you can make this work for the octet rule, remember the octet rule is atoms, elements of atoms, or atoms of elements, got that backwards, atoms of elements want to gain or share or lose electrons, so they have 8 valence electrons. The one exception to that is hydrogen. Hydrogen's octet is 2. Hydrogen's octet is 2. So I have nitrogen with 5 valence electrons, 5 dots. I have each hydrogen with 1. So one hydrogen says to the nitrogen, I have a valence electron, you do, let's share. And they do. And the other 2, because remember there are 3 hydrogens, do the same thing. And that's how you would do ammonia. Now, I'm going to let you try one. Why don't you try oxygen gas? And I will tell you, oxygen has 6 valence electrons. Let's find out if I'm telling you the truth or not. Dr. White makes mistakes. Oh, I'm right. Oxygen, look at the top, 6 valence electrons. And why don't you try doing your turn to do the Lewis structure for oxygen? Okay, my turn. Each oxygen has 6 valence electrons. Now, you don't have to draw this on a test like I'm doing, but I'm showing you the way to think about it. This oxygen has 2 single valence electrons. This oxygen has 2 single valence electrons. So this oxygen says to that one, I've got 2 single electrons. You have 2, let's share. Here are my 2. And the other oxygen said, here's my 2, let's share. And the non-bonding electrons, 2 pair on each oxygen, are still there. And this is your answer. Now, what kind of bond exists between oxygen atoms in oxygen gas, O2? And if you notice, we have 2 pair, which means it's a double bond. Now, I didn't do it for ammonia, even though it's true, but I'll do it now. If we look at each oxygen at the shared and non-bonding electrons, look at that in red, count them, 2, 4, 6, 8. It's got an octet. If we look at the other oxygen, I'll do this in blue, 2, 4, 6, 8. So each oxygen has its octet. If we look at up here, nitrogen, it has 2, 4, 6, 8 shared and unshared electrons. Now, hydrogen, remember its octet is 2. And each one of those does. And that's how you do Lewis structures of molecules. Now, don't forget, all the alkali metals and all the alkaline earth metals like lithium, sodium, potassium, and then magnesium and calcium never form covalent bonds. Those are always forming ionic bonds. So if you see that in a molecule, those alkali metals or alkaline earth metals will always be cations, plus charge anions or plus charge ions. All right, let's move on to moles. You should know a mole is a chemist counting unit. Just like if you go into I don't know, a bakery, baker shop or a bagel shop, you get a dozen bagels. Or if you go to the supermarket, you can't buy one egg. I wouldn't try that. They sell it by the dozen. Now, moles count, a chemist counting unit is the mole. Now, there are important relationships, and those are 1 mole of an element equals Avogadro's number, and this should be superscript. I'll have to change that. Sorry about that. And 1 mole of an element equals Avogadro's number. You should know 6.02 times 10 to the 23rd is Avogadro's number, a great Italian chemist or scientist, I think they call it back then, who was very instrumental in determining what a mole is. And that's why it's called his number. Even though he didn't discover that number, he was instrumental that led up to that discovery. Equals 1 mole of an element equals Avogadro's number of atoms of that element. 1 mole of a compound equals Avogadro's number of molecules of that compound. And also, we know that 1 mole of a compound equals the atomic weight in grams of that element. And 1 mole, I said element, it should have said 1 mole of an element equals atomic weight of that element in grams, and 1 mole of a compound equals the molecular weight of that compound in grams. And remember, the molecular weight of a compound is the sum of all atomic weights. Now, before I go on and talk about remembering to use your good buddy, your good friend, unit analysis, quick commercial from Dr. White. For test 1, it will say underneath your name, please use proper significant figures for all calculated answers. And it will say, please use 3 significant figures for all atomic masses. If you don't do those on a problem, I'll take off a point. You do that enough times, you're going to lose a lot of points. So remember, please use proper significant figures for all calculated answers, and please use atomic masses to 3 significant figures. Now, we were talking about our good buddy, our good friend, unit analysis. So let's take a look at how you use that to remind you. All right, let's do this stepwise, and I'm going to ask for your help. And that is, what are you being asked to find, and what are you given? And when you just figured out those two things, give me a thumbs up. All right, my turn. Well, it says how many moles sodium chloride? And that means you're trying to find moles sodium chloride. You're given how many molecules? Of sodium chloride. So once you have this, you don't have to look here anymore. And now we have this is the only number to work with. So I will. If I had a magic ratio, it's not magic, it's chemistry, ratio to convert this, what units do we want our answer in? Your turn to put that there. And the answer is right here. You figured it out. You want to get to moles of sodium chloride. And now it's time to use your good buddy, your good friend, unit analysis. I love that whistle. And how do you use your good buddy, your good friend, unit analysis? Whatever you're trying to get to, the units go on top of that ratio. Whatever you're trying to get rid of, the units go underneath. So I'll write that in. And where do I get these numbers? Well, it's an important information, but I'll show it to you in the review. 1 mole of a compound equals Avogadro's number, 6.02 times 10 to the 23rd. And whenever you have two things equal each other, you have two ratios you can always form. A over B, and they're not equal, they're separate ratios, B over A. So what's the relationship between moles and molecules of a compound? 1 mole equals 6.02 times 10 to the 23rd molecules. And don't forget, this is Avogadro's number. And now remember, anything divided by itself equals number 1, which means it cancels out. So I have molecules of sodium chloride divided by molecules of sodium chloride. That cancels out. I'm left with moles of sodium chloride. And now I can pick up my calculator. Make sure you practice with your calculator scientific notation. And don't forget, it's second key, double E on my calculator, 45 divided by 6.02, second key, double E, 23. Ha! And the number my calculator gives me is 1.264950,166 times 10 to the 22nd. Remember, when you do a multiplication division, you get the same number of significant figures in your answer that the number you multiply and divide, that has the lowest significant figures. And here we have 4 significant figures, all non-zero numbers are significant. 6.02, 0 after a decimal is significant. So Avogadro's number, 3 significant figures. The 1 is an exact number. And therefore, I should round this off to 3 significant figures. I'll let you do that first, then I'll do it. Round 1.264950166 times 10 to the 22nd to 3 significant figures. And it's my turn. Keep the 1, keep the 2, keep the 6. Use the 4 to round off. That's 4 or less. So I drop all this. And the correct answer with proper significant figures and this is your correct answer. Now, you don't have to put the units down. I always do. And let me tell you something very important to remind you. When you have a problem like this, show your work. If you would just put a number down and you pushed the wrong button on your calculator, even though you knew what you're doing, and say you got 2.85 times 10 to the 15th, wrong number, and you don't show your work, you get 0 points, 0. If you do that and I see this set up and I said, everything's right, but you pushed the wrong buttons on your calculator, I'll only take off 1 point for a math error. So it pays to show your work. Also, I've learned the more you let the paper think when you take a test, in other words, write things down instead of keeping it in your brain, the better your test scores are. And trust me, I've taken more tests by the time I got my PhD than you have at this point in your life. A lot more and a lot harder. All right, let's continue on. Now, don't forget, 1 mole of an element equals the molecular weight of that element in grams, and the molecular weight of a compound is the sum of all atomic weights. And this you will all be given in important information, test number 1. Look in the folder of Blackboard to see what you actually will be given. But when you take test number 1 at the testing center next week, if you look at the last 2 pages, you will see important information. And things like I just showed you will be there to help you. Now, when we talk about moles, important aspect you should know is a chemical equation. And a chemical equation is indicated by an arrow. At the base of the arrow, we have the reactants. I also call them starting materials. And at the head of the arrow are the products. And if you have more than one, they're separated by a plus sign. Think of the plus sign as the word and. Now, because of the conservation of mass law, that you never create or destroy atoms in a chemical reaction, you have to have a balanced chemical equation. That means you have the same number and same type of element on each side. And if you watch yesterday's video, which would be 2022 1011 file name, and you'll see how I showed how to balance chemical equations from the problem set. And you can only change the coefficients. Students like to say, well, if it's H2O, but I need an extra oxygen, I'll make it H2O2. Nope, that's a different compound. That's called peroxide. You can only change the number in front, the coefficients. Now, my advice when you have a complex chemical reaction or chemical equation to balance, leave hydrogen and oxygen last. It works for me. You don't have to, but it makes your life a lot easier. I don't know about you, but I like my life being a lot easier. Also helps you get a better grade on the test. And on test one, there'll be four balanced chemical equations. It's that important in chemistry. Now, remember, if you have an odd and even number of atoms on each side, the trick I showed you, take how many on each side, multiply them together, and excuse me, that's the way you get each on to balance it. And I went through that. Now, one thing I do want to mention, because students do this and it's always wrong. This is the correct balance equation for that reaction. This is the wrong balance of chemical equation. Why is it wrong? Because if you can look at each coefficient and divide it by a number, the same number, and get whole numbers, you should do that. You should have in a balanced chemical equation, you can't divide each of the coefficients by the same number and get a whole number. You can't. However, this one, that's wrong. If you divide each one by 5, then you'll wind up with the balanced chemical equation. So you should never be able to divide the coefficients by the same number to get whole numbers like I just did into the wrong one. Now, remember the coefficients, and when there's no number, it's the number 1. That tells you molar relationships. What this really means is there's 2 moles of hydrogen gas reacting with 1 mole of oxygen gas. As I say, 2 moles of hydrogen gas react with 1 mole of oxygen gas to make 2 moles of water. Remember that relationship. And by using that, you can do the following 2 types of problems. One is mass calculations for reactions. That's where you're given a balanced chemical equation and asked to go from grams to grams, grams of a compound or element to grams of another compound or element. And the only way you can do that is by these 3 steps. And if you go back and look at yesterday's video, which is on YouTube, you'll be able to see how I did those 3 steps. And as I say here again, remember the coefficients of a balanced chemical equation are molar ratios. Now, the last part, one thing I want to talk about for the review for test number 1 that you'll be taking next week at the testing center, and that is what's called limiting reactants. And here you're given a balanced chemical equation and 2 of the reactants. And you're asked, based on the 2 reactants, how much, and I'll keep it to moles, how many moles of product will you make? Well, what you have to do is determine the number of moles the product produces using the moles for each reactant. We went through that yesterday. And then the lowest number of those 2 will be the answer. And that's my review for test number 1. Some advice from Dr. White: do the practice problems. You'll find out, and I think you did from quiz 1 and 2, why I call them practice problems. Go through and do them. Test number 1, my old test number 2, but test number 1 is usually the lowest average of the semester. However, it doesn't have to be, and I've had classes that it isn't. Do the practice problems on your own and then look at the answers. And also, you can also go back and look at the videotapes when I've gone through those. And with that, I'll ask, are there any questions? Well, if I look at the time, it was time for a break. It's almost 9:50s, 9:49 something. So why don't you come back at 9, well, it's now 9:50. I talked long enough to make a change. Come back in 5 minutes, 9:55, and we'll continue on with today's lecture. I'll see you in 5 minutes. I'm back. All right. I hope you found the review useful. And anybody have any questions about any of the material on test one? Clean out my eyes that way. Any questions for test number one? Well, in that case, let's move on. Let me close something first. And then I need to open something. All right, everybody see gas pressure on your screen right now? Oh, I better check. Oh, thank you, Anna. All right, now on Monday, I was talking about gases, and one of the important things you measure, and here key properties of gases, is the pressure. And the pressure, which I'll never ask on a test, is force per unit area or force per unit area. And the key units we use in chemistry, 1 millimeter of mercury, Hg is mercury, and that's equal to 1 torr. And that's given named in honor of the Italian scientist Torricelli, who invented the barometer, which is a way of measuring gas pressure. Now, there's another important concept at sea level, with Chicago, when there's no storm going through, by definition, at sea level, no storm, the atmospheric pressure is 760 millimeters of mercury. This is an exact number. And because 1 millimeter mercury equals 1 torr, therefore, at atmospheric pressure at sea level is also defined as 760 torr. Now, there's another important measurement for pressure or unit, really, and that's called the atmosphere, abbreviated by the letters ATM. And by definition, 1 atmosphere equals 760 millimeters of mercury. And because of this, you also know it's equal to 760 torr. And this you should know. Actually, I should change this how to use, because important information, I've got to change it. What used to be my test 3, and when I normally face-to-face teach 1211, will now be quiz number 3. I'll have this in important information for that quiz. In the past, students would have to memorize it. Good news, you don't. But you do have to know how to use it. Now, there are other units which we will not use. Inches of mercury, which you'll see in weather forecasts, and that's equal to, at sea level, no storm, 29.9 inches of mercury. IN period, or IN is abbreviation for inches. Instead of using millimeters for distance the mercury column in the old barometers would go up, we use the English system, which is inches. Now, just out of curiosity, because I am a curious person, let's look at something. I live in Schaumburg, so this is mine. If we scroll down scroll up a little, you'll see the pressure in right now where I live is 29.69. And if we go back to the slide I just showed you, it's at sea level, which Chicago and Schaumburg and Glen Ellen essentially are, 29.9. How come it's lower? Well, there's a storm that just went through. And if you watch the weather forecasts on TV, you hear them talk about here's a low, here's a high. They're talking about the atmospheric pressure. I'm not a weatherman. I didn't want to. I had never thought of that occupation, although I'm sure it's a very rewarding occupation. But if you watch the weatherman or weather women, which are more likely you'll see on TV these days, you'll see they'll talk about highs and lows. And when there's a storm coming through, the pressure, atmospheric pressure drops. And if you look out my window, and I assume by your house too, it's raining or just rain. And that's going to cause the pressure to be lower. And it was. Now, another important measurement is PSI. PSI means pounds per square inch. And 1 atmosphere equals 14.7 PSI. Now, where you in your daily life will see PSI is your car tires. Think about it. Your car tires have air inside, or some of them also might just have nitrogen gas inside. Remember, air is 80% by weight, nitrogen, 20% oxygen. And my car tires on my Explorer, I have a Ford Explorer, I keep at inflated pressure in the tire at about 35 PSI, almost more than double the atmospheric pressure. Now, I can tell you, I have worked with gases in the lab, and the chemical plants. And I've worked at pressures, very high pressures, and I've worked at usually about 600 PSI. And that's quite interesting. The highest pressure I've ever worked with chemical reaction in the plant, like I said, 600 PSI. In the lab, a couple times I tried some things where I was up close to 1,000 PSI. And that was quite dangerous. In fact, quick story, where I work, one company where we work with very high pressure gases, the equipment you work with, it was called an autoclave. And hold on, let me see if I can show you a picture of one. Everybody see on the screen, pressure hydrothermal autoclave reactor. I've worked with those type, and like this, the larger ones, it's quite exciting. I've worked with one like this, and the smaller ones like this one right here. And the setup we had was this type of setup with the heater and everything. Our heater was a little older than it was fixed. But here's the type of autoclave was my friend. No, if they don't show a good picture. And this one right here. And you see a gauge on top. You see the big round gauge here? I have my pointer. That's always in PSI, pounds per square inch. You can't, let's see, they have a good picture of one? Not really. But anyways, these type of reactors like right here, we would work in the lab, and you didn't work in the actual lab. We had a special high pressure lab because working at high pressure gases is very dangerous. It could blow up or and even though the reactors were very thick walled, they had what was called a rupture disk. If you got above a certain pressure or got too high and dangerous, instead of the reactor blowing up, it'd be like a bomb going off and kill you. They had a rupture disc, a special metal that at a certain pressure blew out. You had a hose, and a metal hose went to a pipe, and that went to the roof of the building. So if it blew out, it sprayed up there where nobody was and got out in the atmosphere and was diluted and safe. Now, in this lab, we had cubicles, and each one was made of, each cubicle, about half my bedroom here, had steel plate walls that was this thick, and the door was that thick, solid steel. Nothing would penetrate that. But the back wall, it was on the ground floor, had what was called a blowout wall. If you thought something was going to happen, you just backed up and smashed into the wall and it'd break away and you could get out quick. But when you were working or running a reaction, you'd close the door so something happened. Luckily, nothing ever happened. We had a few close calls, not me personally. And after I became section head of process and product development for that company in that research building, one of my jobs, besides supervising my own research group, was to supervise the high pressure lab, which all the research chemists, even outside of my group, use. And it was quite an interesting lab. That's because you were at very high pressures with the gas. We were working with hydrogen and ammonia. All right, so again, remember, 1 millimeter mercury equals 1 torr. And at sea level, the pressure, atmospheric pressure, no storm, 760 millimeters of mercury, which is also defined as 1 atmosphere. So you know what that means? It's pressure practice time. And let's look at a couple of these. Let's look at the first one. How many torr is 452 millimeters of mercury? So how do we do this? What are we being asked to find? Torr. What are we given? (452 millimeters of mercury. This is the only thing we have to start with. If I had a ratio, what units do I want my answer to be in? And that's torr. And guess what time it is? Nope, it's not just for one chapter. It's for the rest of the semester. You should know it's time for your good buddy, your good friend, unit analysis. And how do you use your good buddy, your good friend, unit analysis? Whatever you're trying to get to goes on top of the ratio. Whatever you're trying to get rid of goes underneath. And now I'll write those units in. Torr. And where do I find a relationship between torr and millimeters of mercury? Well, if you look at important information quiz 3, which I don't have yet on Blackboard, that's this week's job or weekend. But up here it says 1 millimeter mercury, and Hg is the chemical symbol for mercury, equals 1 torr. So now I know that relationship. I can come back here and put 1 torr equals 1 millimeter mercury. These are exact numbers because they're part of a definition. And notice millimeters of mercury cancel out. Anything divided by itself equals number 1. This is 3 significant figures. My answer should be, this is an easy one, some number divided by, multiplied times 1 divided by 1 is that same number. So the answer would be 452 torr. Now, let's come down here and do the next one. How many atmospheres is 832 millimeters of mercury? So what are we trying to find? Atmospheres. What are we given? 832 millimeters of mercury. And the only number we have to work with is this. If I had some ratio, what units would I want my answer to be? And we figured that out. Atmospheres. And now it's time to use our good buddy, our good friend, unit analysis. Whatever I'm trying to get to goes on top. Whatever I'm trying to get rid of goes underneath. And I'll write those units in. And if we look above, but I'll write it right here, (760) millimeters of mercury, by definition, these are all exact numbers, equals 760 torr equal 1 atmosphere. Therefore, from this, I know 1 atmosphere is 760 torr. And remember, this is a defined number. 1 is an exact number. 760 is also defined exact number. And now, before I pick up my calculator, notice millimeters of mercury divided by millimeters of mercury cancel out, and I'm left with ATM, atmospheres. And now I can pick up my calculator, clear it first, and say 832 divided by 760. And my calculator gives me this number. And the question is that correct? No, because you'll have on quiz 3 and the rest of the semester, you'll always have on test or quiz, please use proper significant figures for all calculated answers. This is 3 significant figures. All non-zero numbers are significant. These 2 are exact numbers, so we have to round this off to 3 significant figures. Keep the 1, keep the 0, keep the 9. Those are my 3 significant figures. And the one to round off is this number. Is that 4 or less? Duh, yes it is. It's 4. So I drop all that, and the correct answer is 1.09 atmospheres. And again, use your good buddy, your good friend, and also this relationship or definition really, 760 millimeters of mercury equals 760 torr equal 1 atmosphere. Now, I'm going to let you try this one. We'll do it stepwise. And first of all, what are you being asked to find and what are you given? And the question reads, how many atmospheres is 777 torr? So when you figure out what do you asked to find, what are you given, give me a thumbs up. All right, my turn. You're asked how many atmospheres, and something like this would be 3 points each. Hint, we're trying to find how many atmospheres, and we're given 777 torr. And once I have this, I never have to look at the problem up here again. Now, there's only one number we have to deal with. That's that. If I had a ratio, what units would I want there for my answer? And the answer is ATM. Now, I'm going to let you do 2 steps at once. What units and what number go on top and below that ratio? And hence, don't forget to look here. Your turn. All right. Well, it's time to use our good buddy, our good friend, unit analysis. Whatever we're trying to get to unit-wise goes on top. Whatever we're trying to get rid of goes underneath. So I'll write those in. And where do I find a relationship between atmospheres and torrs? Right here. Notice 1 atmosphere equals 760 torr. Also equals 760 millimeters of mercury, but we're not using that. And now you can see at torr divided by torr cancel out because anything divided by itself equals the number 1. And I will remind you the 1 is an exact number. The 760, because this whole thing is a definition, is an exact number. But this is 3 significant figures. And now I can pick up my calculator, clear it. 777 divided by 760. And my calculator gives me this number. And that I would take a point off if you wrote that down in a quiz or test, because that should be 3 significant figures. So I'll let you round that off to 3 significant figures. Then I will. Your turn. All right. Keep the 1, keep the 0, keep the 2. That's my 3 significant figures. Use the 2 to round off. Is that 4 or less? Yes. So I'm going to drop all that. And the correct answer is 1.02 atmospheres. ATM means atmospheres. Now let's do one more. But first, let me clean this area up. And you can go back and look at the video of what I'm erasing in case you need to see it again. And in real life, if we had been face to face, you'd be watching me erase the whiteboard. All right, we got a clean surface to work with. Let's do one more. And let's do the last one. Let me first get rid of this. And why don't you try this one all by yourself? How many torr is 2.1 atmospheres? Set it up. Use your good buddy, your good friend, unit analysis, but I will give you one hint. Take a look at that. And don't forget, tonight from 6 to 7:15 on Zoom, I will have my office hours. If you have any questions, come on by. Remember, use your good buddy, your good friend, unit analysis. Hang on, I got to answer. Sorry about that important phone call. All right, are you done yet? If you are, give me a thumbs up. Or if you want me to proceed, give me a thumbs up. All right. So the question is, how many torr is 2.1 atmospheres? So what are we being asked to find? Torr. What are we given? 2.1 atmospheres. So, excuse me, the only thing we have to work with is this. And if we had a ratio to convert this atmospheres, what units do we want? Our answer. Well, we figured that out. Torr. So it's now time to use our good buddy, our good friend, unit analysis. Whatever we're trying to get to goes on top of the ratio. Whatever units we don't want in our answer we're trying to get rid of goes underneath that ratio. So now I'll write that in. And where do I find that relationship? Right here. 1 atmosphere equals 760 torr. And these are both exact numbers. And notice this number right here is two significant figures. So in a multiplication division, my answer should have two significant figures. Now, before I pick up my calculator, oh, I shouldn't have picked it up. But anyways, notice atmospheres divided by atmospheres cancel out because anything divided by itself equals the number 1, cancels out. And now I can pick up my calculator, clear it, 2.1 times 760, whoops. And my calculator gives me this number. And now this one's a little tricky. Oh, no, it isn't. I was thinking of another number. But anyways, this would be incorrect. Why? Because our answer should have two significant figures. Because 1 and 760 are exact numbers, do not play a role in this calculation. So how do we round this off to two significant figures? Keep the 1, keep the 5, use the 9 to round off. Is that 5 or higher? Yes. So I'm going to drop that, and anything afterward, because we're past the decimal, the number in front, I'll increase by 1, and the correct answer is this. On your calculator, don't forget, there's a little 10, at least on mine, x10, then number like here, I don't know if you can see it, probably not, 0.3. And that's 10 to the third. And that's how you do this. So you should make sure you know how to convert from torr to millimeters, millimeters to torr, and from atmospheres to millimeters of mercury or millimeters of mercury to atmospheres, and from torr to atmospheres or atmospheres to torr. And what do you use? This right here. This will be given to you for quiz number 2. Number 3. All right, let's move on. First of all, this is thirsty work. Gases play an important role in our life, especially in industry. And long ago, about the 1700s, what was very important? The Industrial Revolution. And if you don't know your history, go back and read about it. It's quite an exciting time in the world. And where was the greatest advances in the Industrial Revolution occurring? In England. And what was the big advances? How to use different sources of power to operate machinery that did things by machine instead of just doing it by hand. Example would be making cloth. Some of the mills that made cloth and thread in England, how were those powered? The machines they had invented to do that. Well, first it was the water wheel, and then it was the steam engine, and finally the gas engine. And those are all very important advances. Now, part of the thing that helped England and the rest of the world use gases for a source of power were certain mathematical relationships that were discovered in England and by scientists there. And those are called the gas laws. A law in science is something that's always true. There's no exceptions. A law in science is always true. And the gas laws are mathematical relationships that are always true under the conditions of those laws. And the first law I'd like to talk about, oh, by the way, steam engine, let's do something first. Can everybody see how the steam engines work on the right side of your screen? Let's see if I can get a better picture of this. Now, hold on. Time out for commercial. Everybody see the train engine on your screen? Thank you. If you look at the lower left, you'll see it has a small picture of a piston that's right here that goes up and down and runs this lever right here. And the heat here from the steam causes that valve to go up. When it's released, it comes back down. And inside is steam. What's steam? Hot water in a vapor phase. In a vapor, we mean a gas. So the steam engine dealt with water, this stuff right here, but in a gas form. By heating it, you could make something move, and then when you release it, it would go back down. So go up and down using the gas of water, steam. And it helped to know relationships of what's happening in that cylinder. Oh, by the way, your car engine uses the same principle, but instead of steam, it uses gasoline, which is ignited to form a gas to push the cylinder out, the piston in the cylinder out. Well, the first law that I'm going to talk about is called Boyle's law. And Boyle, and I don't know if he was Dr. Boyle. Hold on, we got time. I've never done this. Inquisitive minds want to know. Here's Robert Boyle, obviously, like I said, around 1700. He died in 1691. So the late 1600s, he discovered, and notice he was a natural philosopher, chemist, physicist, alchemist. I don't know what's the difference between an alchemist and a chemist, other than alchemists maybe do pooky stuff too. But anyways, he is best known for Boyle's law. Oh, here's a pretty picture. Everybody see that cylinder going up and down? And what's changing is the volume and the pressure. The temperature is kept the same. And Boyle's law deals with, in a cylinder, the relationship between volume and pressure of a gas. Wow, that's a pretty animation too. All right, now I will never ask you what in words is Boyle's law. And Boyle's law is the volume of a sample of a gas is inversely proportional to the pressure applied to the gas if the temperature is kept constant. And I won't get it today, but Monday, remember the hand pump. Now, Boyle's law is P1 times V1 equals P2 times V2. And what's P1 V1, P2 V2? Well, P1 is the initial pressure. V1 is the initial volume where you start from. And P2 is the final volume where you end up, or final pressure, I'm sorry, got ahead of myself. And V2 is the final volume. So we have Boyle's law, P1 times V1 equals P2 times V2. Now the initial P1 is the initial pressure, V1 is the initial volume, and P2 is the final pressure, and V2 is the final volume. Now for Boyle's law, and it's not true for all laws, but for Boyle's law, the volume and pressure can be in any units. And what are volume? Well, pressure units, you've already seen. Pressure can be atmospheres, millimeters of mercury, or torr. Volume, and this is always in the metric system. I don't know about the English system, I've never tried it, but is usually going to be in liter. It could be milliliters, but I'm going to stick to liters, and that's abbreviated by the letter L. So Boyle's law, P1 V1 equals P2 V2. Now, in a Boyle's law problem, you'll be given three of these variables, such as P1, P2, and either P1, V1, and either P2, and then you'll calculate V2, or you'll be given V2, and you'll calculate P2. Now, take a deep breath, relax, take a deep breath, relax. Let's do one more. Take a deep breath, relax. Now, we're going to do, stay relaxed, some algebra to solve that kind of problem. And I won't get to it today because we're just about out of time. But on Monday, I'll go through some of these problems and you'll get the hang of it. Relax. All the math you have to use in my class, I will teach you how to do and use to solve problems. And my students do good as long as you practice on your own. Because remember, I talked about the bicycle. If you watch the Blu-ray, How to Ride a Bicycle, and never been on a bicycle, first time you get on a bicycle, boop, you fall off. I don't know if you go boop, but you fall off. I like that my eyes watch. Boop. I guess that's wired into my brain. But anyway, oh, it's totally silly Wednesday too. But anyways, do the problems, watch me how I do it, and you'll do okay. Now, if I look at the clock, we're just about out of time. I may end about 2 minutes early. But remember, important things. Tonight, 6 to 7, 7:15, I'll have my office hour. Next week, Monday through Thursday, you need to go to the COD, College of DuPage Testing Center in Glen Ellen, not the other testing centers, only the one in Glen Ellen, and you'll have to look up what their hours are for those days. I don't remember them right offhand, but anytime they're open, Monday through Thursday. Get there about an hour, hour and a half early before they close. You'll take test number 1. Now, because I was thinking about this morning, you might be distracted by people coming in and leaving the room. I've given you 90 minutes to take test number 1. When I give it face to face, Students get 50, 55 minutes max. So you got plenty of time, relax, do the problems. Remember, at the last 2 pages, we'll have important information. Also, remember to ask, if they don't give you one, to give you my periodic table. It's in my instructions to them, but still, things happen. They, might be busy, and the man who's helping you out there might forget to do that. But if you don't get a separate periodic table when they give you the test, ask for it. Also, the test should have 9 pages, 7 pages with problems, I believe, and 2 pages with important information. Check to make sure each page has it. I asked them specifically, print it on one side only, not in both. It's easier for me and you to take the test and me to grade it. And with that, I'm done for today. We're done for the week, except for my office hour tonight. And with that, I'll say, do the practice problems between now and next week before you take test number 1. And I hope you all do well. Don't forget, you need a picture ID and bring your calculator. They have some, but I would always bring my own because I know how to use my own. The others, they should be the same, but you never know. With that, I will say, gang gesund. Bye now. Stole that from Granny to Beverly Hillbillies. Gang gesund. Bye.